Our oceans, covering more than 70% of our planet's surface, are a magnificent expanse of mystery and wonder. They are home to an astonishing diversity of life, from the tiniest plankton to the largest whales. But beyond their beauty and biodiversity, the oceans play a crucial, often overlooked role in sustaining life on Earth. They act as one of our planet's most vital carbon sinks, absorbing approximately 30% of the carbon dioxide we release into the atmosphere. This incredible process begins with the smallest of organisms, phytoplankton, derived from the Greek words phyto, meaning plant, and plankton, meaning drifter. They are microscopic organisms living in watery environments. And like land plants, phytoplankton play a crucial role in the carbon cycle. During photosynthesis, they consume carbon dioxide, incorporating the carbon into their own structure and releasing oxygen into the water. As primary producers, when phytoplankton are eaten or decomposed, most of the carbon is returned to near-surface waters. But some of it sinks to the ocean depths in the so-called biological carbon pump. During this process, about 10 gigatonnes of carbon are transferred from the atmosphere to the deep ocean each year. As the impacts of climate change become increasingly evident, scientists are exploring innovative ways to face this global challenge. Could the enhancement of phytoplankton growth result in larger quantities of carbon dioxide being absorbed in the oceans? Ocean iron fertilization is a geo-engineering strategy that involves increasing the supply of limiting nutrients, like iron, to surface waters. This crucial micronutrient is used as an enzyme cofactor in photosynthesis. Iron is dissolved as ferrous sulfate in acidified seawater and pumped into the ocean behind a moving vessel. In nature, iron enters the ocean through dust blown from land or via river inflows. However, in remote parts of the ocean called high nutrients low chlorophyll regions, like the Southern Ocean, the Central Pacific, and the Arctic Pacific, iron is scarce. In the late 1980s, geological records revealed a link between Earth's temperature and oceanic iron levels during glacial periods, leading to the famous ocean iron hypothesis by oceanographer Jean Martin. Give me a half tanker of iron and I will give you an ice age. This idea suggested that iron fertilization could boost phytoplankton growth and increase carbon sequestration. While promising in theory, iron fertilization is controversial due to the potential environmental risks, scientific uncertainties, and ethical concerns. Over the past few decades, scientists have embarked on more than a dozen daring researches. Some expeditions, like the Southern Ocean European Iron Fertilization Experiment and the Subarctic Ecosystem Response to Iron Enrichment Study, have yielded promising results, revealing the potential for significant carbon sequestration in the ocean depths. Yet, challenges abound. Many others fail to detect significant carbon export below 100 meters. Estimates show that 1,000 metric tons of carbon are absorbed per metric ton of iron introduced, far less than the higher range of 30,000 to 110,000 metric tons observed in laboratory or natural settings. Can we truly rely on this method? Despite mixed results, the potential of ocean iron fertilization awaits those brave enough to explore. In the attempt to face the rising tide of carbon dioxide emissions, proponents of ocean fertilization suggest a bold solution: By continuously enriching high nutrient low chlorophyll regions with iron, they predict a massive achievement: the removal up to 45 gigatonnes of carbon dioxide from the atmosphere by 2100. But the implications go far beyond just carbon capture. Delving into the intricate web of marine ecosystems, proponents speculate on the exciting possibility through the simulation of phytoplankton blooms. At the core of the ocean's food web, these microscopic organisms are the key to a cascade of benefits, potentially boosting fish stocks and revitalizing commercial fisheries in nutrient-poor regions. As Sir David King, former professor of chemistry at Cambridge University, puts it, in a relatively short time, we can be sure that billions of fish will feed on these organisms, and the oceans will be repopulated. Leading the effort are researchers from the Alfred Wegener Institute for Polar and Marine Research and the Woods Hole Oceanography Institution. Alongside them, environmental NGOs such as the Environmental Defense Fund lend their support for further research. With the promise of cost-effective carbon sequestration, ocean fertilization emerges as an attractive strategy. With the low cost of iron and the potential for carbon sequestration, it represents a compelling solution for reducing CO2 levels into the atmosphere and charting a course towards a more sustainable future. Yet, in the depths of the ocean, a dance between hope and uncertainty unfolds. Is this delicate balance truly as simple as it seems? How long does carbon stay sequestered in the deep sea after iron fertilization? Which are the side effects? The growth of phytoplankton does not always result in significant carbon export to the deep ocean. Dr. Christian Merz, associate professor in biogeochemistry at the University of Leeds, said, most of the dead algal biomass get degraded within the top 100 meters of the ocean, eaten up by microbes, and most of the sequestered carbon dioxide gets returned to the atmosphere. What happens when iron is introduced into the ocean? It is a catalyst for change, which is expected to increase the population of larger phytoplankton while exacerbating ocean acidification, especially in regions such as the subantarctic Southern Ocean. Here, the intricate equilibrium shifts when the smaller phytoplankton, known as diatoms, which depends on silicon for their skeletal structure, suffer a collapse. Increased phytoplankton growth absorbs CO2, which turns into a weak acid when it mixes with seawater, making deeper waters increasingly acidic. This acidity reduces the ability of some marine organisms to produce the vital carbonate shells on which they rely for survival. Therefore, iron fertilization may disadvantage diatoms, setting in motion changes within the ecosystem. Increasing the biomass of phytoplankton near the surface could also cast a shadow over the deeper realms, depriving corals and algae of the sunlight they crave, while at the same time triggering an oxygen depletion in the depths, creating dead zones in which marine life struggles to survive. The question that arises, is this a risk worth taking? In 2021, a report from the U.S. National Academies of Sciences unveiled a sobering truth. Large-scale iron fertilization could trigger a 5% drop into the biomass of fish and marine species in tropical regions, adding to the anticipated 15% decline to climate change alone. Despite confirming the potential for iron fertilization to remove up to 45 gigatonnes of CO2 by 2100, these figures pales in comparison to the emissions reductions needed. Moreover, modeling research from 2020, led by oceanographer Jonathan Lauderdale from the Massachusetts Institute of Technology, suggested that while phytoplankton blooms in the Southern Ocean might absorb excess nutrients, it could also disrupt food chains, with fewer blooms occurring elsewhere. He advocates for further investigation into iron fertilization. Environmental advocates, including Greenpeace and the ETC group, raises concerns over the potential for unpredictable and irreversible adverse impacts on marine ecosystems posed by iron fertilization. They advocate for a shift toward reducing carbon emissions at the source, rather than relying on geo-engineering techniques. From an economic perspective, the initial perceived low-cost estimates of iron fertilization were biased by optimistic assumptions. The National Oceanic and Atmospheric Administration report says the iron fertilization has low to moderate potential compared to other ways of storing carbon into the ocean. It also faces difficulties in being scaled up to a global level, making it harder to apply widely. While iron fertilization could help store carbon, it might be not as effective or practical as other options. In the midst of this debate, one thing is clear: there are no easy answers. Each carbon dioxide removal strategy presents its own set of challenges and uncertainties. Perhaps, as Dennis McGallincuddy from the Woods Hole Oceanographic Institution suggests, they are all pieces of a larger puzzle. Almost all of them have the potential to have unintended consequences, but also intended ones. As we navigate these complexes, one question lingers: should we proceed with caution? Since the early 2000s, organizations such as the International Oceanography Commission and the Intergovernmental Panel of Climate Change, along with several legal conventions like the UN Convention on the Law of the Sea and the Convention on Biological Diversity, have shown a keen interest in this practice. In the course of this exploration, the London Convention Protocol has emerged as the main framework for regulating iron fertilization, given its focus on the delicate balance of substances introduced into our seas. This framework seeks to regulate and supervise the disposal of materials into the sea, safeguarding pollution. By defining ocean fertilization as the introduction of matter for a purpose other than simple disposal, the protocol sets a clear directive for the management of our ocean environments. At the heart of this framework is the holistic approach to environmental assessment, a path that digs deep into the heart of ocean fertilization proposal. Through meticulous risk analysis, site selection, exposure and effects assessment, the protocol ensures a comprehensive understanding and the minimization of potential impacts on marine ecosystems. Furthermore, international collaboration weaves a powerful web around the protocol, which invites parties to consult with affected states and promotes cooperation and addresses knock-on effects across borders. Continuous vigilance and monitoring of activities ensure that marine habitats thrive in harmony. Yet, challenges persist. With only 45 of the potential 200 contracted parties signing on, notably non-participants like the United States and Russia, and with more jurisdictional boundaries that exclude the high seas and ships flagged non-parties, the journey to compliance remains rocky. What does the future hold for ocean fertilization? The Committee on Geo-Engineering Climate has identified the crucial directions for these studies. How effectively Do iron inputs stimulate the production of biological organic carbon and enhance carbon export in our oceans? What are the downstream effects of iron fertilization? How do we detect and account for changes in subsurface ocean carbon sequestration? Researchers must investigate the decomposition rates, the depth of carbon sequestration, and the duration for which carbon remains trapped into the ocean depths. In our quest for knowledge, we turn to nature for guidance. Natural iron fertilization events in the Southern Ocean, where iron is naturally supplied to the upper ocean throughout processes like sedimentary resuspension, island runoff, and glacial melt, provide valuable insights. These natural phenomena provide a window into the resilience of ecosystems subjected to iron enrichment, offering clues to the potential impacts of large-scale fertilization efforts. But amidst our exploration, current knowledge from natural iron fertilization studies is still insufficient to provide definitive guidance to governments. Can these natural experiments truly inform future geoengineering strategies? And do we have enough knowledge to guide governments on the efficacy and safety of ocean fertilization as a CO2 mitigation strategy? As our exploration of ocean fertilization draws to a close, we stand on the brink of discovery and responsibility. With each discovery, the urgency of our mission grows, and within the mystery of the ocean depths and the uncertainty of our future lies an undeniable truth. The fate of our ocean is a reflection of our commitment